Lydia Zakynthinou, also from the ML pod. Should we?
I'll take it out just again.
Yeah. How do you pronounce it?
Zakynthinou. Okay. Yeah, let's try it. I'm not sure if it worked.
Okay. Okay.
Yes. Okay. Apologies for the delay. Let's see. Does this work? Okay, thank you. So I'd like to tell you about the connection between robustness of data corruptions and differential privacy, which this paper was joint work with Hilala Assi and Jonathan Allman. So we're thinking about the general setting of statistical estimation where we have some distribution D. We want to learn a specific parameter of that distribution. Think of the mean for simplicity. And so what we want is an algorithm which, given training data X, returns something that is close to this parameter that we want to estimate. And so two very common desiderata of machine learning algorithms are differential privacy, which says that in the process, I shouldn't leak too much information about the training dataset X. And robustness of data corruptions, which says that even if someone corrupts a part of my dataset, the output should still be somewhat accurate. And a bit more formally, just to introduce the parameters, epsilon differential privacy says that if I have a pair of datasets, two datasets that differ on a single data point, but are arbitrary otherwise, the probability that I see any one output under dataset X should be close to the probability that I see the same output under dataset X prime. So my algorithm's output shouldn't change too much if I change 1 point in my training data. And epsilon measures the privacy loss. The smaller epsilon is, the more private my algorithm. Now, robustness says that If I draw a typical sample X, not worst case this time, just a well-behaved sample from a distribution D, but someone, an adversary, comes in and corrupts a fraction tau of my data points, then the output of my algorithm should still be accurate on any corrupted data set. So the output should still be close. And I measure the accuracy with alpha of tau because the accuracy of the robust algorithm will depend on the fraction of corruptions in its input. And so the two notions, you can tell how they're intuitively close. They say that the algorithm should be insensitive to changes in its input, but formally they're quite different. What we've known for a long time is that differential privacy seems like a stricter notion. It says we know that epsilon differentially private algorithms are inherently robust to a small fraction of corruptions. But in the other direction, things were more fuzzy. We had several optimal differentially private algorithms in the literature that the way people came up with them was by being inspired by the equivalent robust algorithm for the task. But in a general, tailored way to every task at hand. So what we did is ask the question, can we come up with a systematic way to take any robust algorithm and turn it into a differentially private one? And this is the punchline of this work. The answer is yes. Given black box access to a robust estimator, you can always construct an epsilon differentially private estimator for the same task. Maybe that's not the surprising part. The surprising part is that you can relate the accuracy of your differentially private estimator to the accuracy of the robust estimator. And specifically, the accuracy of the epsilon differentially private estimator we construct is the accuracy of the robust estimator for a specific number of corruptions. And you don't have to care about the specifics right now, but the number of corruptions depends on the size of the parameter space and the number of points and the privacy loss. So the good thing about this is that this is a general transformation. It works every time. And the accuracy guarantee, actually we can show that tells us that the transformation is not lossy. So in low dimensions, the differentially private algorithms you get from this, we can prove that are always optimal. And in high dimensions, we can show that there are several problems for which the transformation is optimal. So it gives you an optimal differentially private algorithm if you start with an optimal robust algorithm. And finally, we can get like a more general conceptual result between the equivalence between epsilon differential privacy and log n over epsilon n robustness, in the sense that the minimax error that you can achieve under both conditions is exactly the same for low dimensional tasks. Thank you very much. Let me know if you have any questions.
Thank you very much. Maybe we'll take a short break now and meet here again at 3:15 for the next session. Thanks again.